Hi everyone, welcome to the e-content on tensor analysis. So to give a brief outline about the e-content, this session is going to start with an introduction about tensor, with an n-dimensional space and with the coordinate transformations, with few summation conventions, that two Einstein conventions, with some introduction about some indices which is used in tensors, and two broad categories of tensors, contravariant and covariant vectors, and with different types of tensors called symmetric and antisymmetric tensors. Okay, what do you mean by the tensor? Tensors are nothing but they are the mathematical objects that generalize scalars, vectors, and matrices. So to give a simple example, we all know that scalar has got only magnitude and no direction. So scalar can also be represented as a tensor with a rank 0. Hope you could understand. Similarly, vector which has got both magnitude and direction is represented as rank 1 tensor. What do you mean by rank here? Rank is nothing but the degree of the tensor. As we use the terminology rank to find the rank of the matrix depending upon the rows and the columns of the matrix, here the terminology rank is referred as the degree of the tensor. So hope you could understand. What is rank 0 tensor? Nothing but a scalar quantity. A vector quantity will always have a rank 1 tensor. So tensors are nothing but they are the mathematical objects that generalize scalars, vectors and matrices to higher dimensions. Okay, so a good example to understand about the tensor is a physical parameter called pressure, which is usually referred as a scalar quantity. The related tensor quantity is stress tensor. So stress tensor is nothing but the tensor which is having a rank 0, which represents the parameter, physical parameter called pressure. And as we all know about the vector space, tensor also has got tensor field which corresponds to each point space. So tensor field has a tensor that is corresponding to each point space. For example, a stress on a material such as a beam in a bridge, or the strain tensor, or the conductivity tensor, or the inertia tensor. So these are the few examples to understand about the generalized term called tensor. And what do you mean by n-dimensional space? Where this n-dimensional space is? We usually use the Cartesian coordinates to represent a point in a space. For example, x, y, z. X, y, z are the Cartesian coordinates which we use to represent a point in a space. In a similar way, we can also make use of suffixes which it is given as x suffix 1, x2, x3 up to xn. So what are these suffixes? Either this can be used as a either it can be used as a subscript as well as superscript. But actually they are not the powers of the variables, but they represent the coordinates of the point in the space. As we represent x, y, z a point, here instead of x, y, z, we are using the integers 1, 2, 3 up to n. So any tensor has got n-dimensional space, which is nothing but n coordinates. Hope you could understand. Yes. So n-dimensional space is defined as the collection of points that satisfies the equation. Okay, right. So what do we do? Coordinate transformations. We do have got barred system and unbarred system with us. What do we mean by barred and unbarred? Barred systems are usually represented with a line at the above, x1 bar, x2 bar, x3 bar. This is nothing but as if we do have got different coordinate systems in mathematics. Cartesian coordinates, polar coordinates, cylindrical coordinates. Here in tensors, it is broadly divided into two categories, barred and unbarred. So if you are able to write a tensor in one system, there is a provision called coordinate transformations can be done from one system to the other system. For example, if you are writing the tensor for unbarred system, so if you want to transform those equations, those tensors to barred systems, then there is a provision called transformation equations. Okay. And what do you mean by summation conventions? Summation convention is nothing but any index which is used either as a subscript or superscript will always take the value starting from 1 to n. So in specific, Einstein summation convention is used. What do you mean by Einstein summation convention? If any index is repeated in a term, then summation with respect to that index over the range starting from 1 to n is applicable. This convention is called as Einstein summation convention. So I repeat, if any index is repeated in a term, then a summation with respect to that index over the range 1 to n is applicable. This convention is called as Einstein summation convention. So there are two different indices. One is dummy index, the other is real index. What do you mean by dummy index? Any index which is repeated in a given term so that the summation convention implies a dummy index. If any index is repeated in a given term, hope you could see the equation here. Dou dx bar is equal to dou x bar mu by dou xk into dxk. So here the index called k is repeated again. So if any index is repeated again, then that index is called as dummy index. And there is also another type of index called real index. Any index which is not repeated in a given term is called as a real index. So here there is an example to understand. And Kronecker delta symbol, which is a well-known delta symbol which we use it in chemistry as well as in physics to represent the properties of delta. So here the delta symbol can also be represented in terms of tensor. So here there is an example for you. Delta jk. If j and k are equal, then it takes the value of 1. If j and k are not equal, delta takes the value of 0. So the properties of Kronecker delta can also be defined here with respect to the properties of free indices as well as dummy indices. And there are two broad types of vectors. One is contravariant vector or contravariant tensor. The other is covariant. What do you mean by contravariant? For example, you consider a system which have got n quantities starting from a1, a2, a3 up to an. So this system of n quantities are considered in a system of variables called xi. Let all these quantities have the value a bar 1, a bar 2, a bar 3 up to a bar n in another coordinate system of variables called x mu. So I do have got two systems now. One is the system with xi, the other is with the system x mu. So if the transformation relation a bar is equal to dou x bar mu by dou xi is equal to a satisfies, then the components of ai are said to be the components of contravariant tensor, contravariant vector. Since here index it consists of only one variable, it can be referred as contravariant tensor of rank 1 or first rank. Similarly, covariant vectors, if I do have got two systems, one is with a system of variables xi, the other is with a system of variable x bar mu. If the transformation equation applies like a bar is equal to dou xi by dou x bar mu into a mu, then the quantities of aj are said to be the components of covariant vector of rank 1. Since here we have used only one index, the rank becomes the 1. So contravariant and covariant vectors will help us to transform the equations from one system to the other system. Positively, not only with the one rank, it can be extended to the higher rank starting from 2 variables, 3 variables up to n variables. And there are two different types of tensors called symmetric and antisymmetric. So if the indices are same for two tensors, then it is called as a symmetric tensor. If the indices are different or if the order of the indices are different, then it is an example for antisymmetric tensor. Even if the order of the index changes, then it should be accompanied with a negative sign indicating that it is an antisymmetric tensor. So in the next class, we'll look into about the algebraic operations of tensors, continued with the outer product and the inner product, and few other applications of tensors. Thank you.